Мелом это плохо. 2, ну ладно. А, тут даже 3, ну ладно, может и хватит действительно. Okay, so at the previous lecture we began to discuss the continuity of the functor k0. So let's call the statement of our theorem. So suppose we have an inductive system of C-star algebras, AI, phi, ij. And we take the C-star inductive limit, we denote it by A. And let's denote by phi I the canonical morphisms from AI to A. Canonical maps, which are already in the definition of the inductive limit. So we apply the functor k0 and observe that k0 of A, first of all k0 of aj, this is an inductive system of abelian groups. Inductive system in abelian groups. And k0a is an inductive cone, just by the commutativity of the respective diagram. An inductive cone over this system. So by the definition, there is a unique morphism from the inductive limit of these groups to k0a, which makes the respective diagram commute. So let me probably draw it here. So I'd like to keep there is a unique morphism alpha from here to here, such that the respective diagram, this diagram commutes for every I. And I claim that alpha is an isotropic. Canonical maps from the groups in the system to their inductive limit. We proved some lemmas. I'll not recall you the exact statements now, because basically, if I'm not mistaken, they were lemmas 1, 2, and 3. They reduce our situation to the unital setting. Is true in the unital case, then it is true for all inductive systems. Of C-star algebras. This, we may assume from now on that all our algebras AI are unital, and all the morphisms phi ij are also unital. All aij are unital, and phi ij are also unital. So this easily implies that the inductive limit is a unital algebra, and the canonical maps phi I from AI to A are also unital. Okay, and all morphisms phi I are also unital. We approved one more lemma. Let's recall it now, lemma 4, which is a technical result about the invertibility in the inductive limit. It states that if A is an element in AI, then its image in A is invertible, even only if there is an index J, which is greater than or equal to I, such that phi ij of A is invertible in A J. So let me draw a picture which represents this situation. So this is phi I and this is phi ij. So of course the right to left implication is obvious, because if the image of this element is invertible here, then its image here is also invertible, but this is exactly phi I of A by the commutativity of the diagram. So the right to left implication is obvious, and the main part of the lemma is to prove the left to right implication. This was done. Okay, so let's now continue our proof. Lemma 5 is about approximating unitaries in the inductive limit. It states that the unitary group in A, in the inductive limit, is the closure of the union of the images of the unitary groups in the algebras AI. That is, every unitary element in A can be approximated by the image of a unitary, of a suitable unitary element in a suitable. Well, first of all, let's observe that the right to left inclusion is clear. Well, indeed, phi I is a unital homomorphism, so it takes unitaries to unitaries. Since the unitary group is obviously closed, it follows that this closure is contained in here. So the point is to prove the opposite conclusion. So we take a unitary element, little u, in A, and a positive epsilon. So for convenience, we assume that epsilon is less than 1. Well, it's a simple exercise to show that if we have an element C satisfying this inequality, then C is invertible. Well, actually, we know this in the case where U is equal to 1. This is one of the basic results about invertible elements in the Banach algebra. So this is true if U equals 1, and in the general case, we simply multiply this by U star, and we deduce that U star C is invertible, and this implies that C is invertible. So this is a very simple exercise. Okay, now, as a first step, I claim that we can always find delta. I may assume that delta is less than epsilon, such that if C is close to U, then the absolute value of C inverse is, this is less than delta, and then this element is less than epsilon. This is true simply by the continuity of this function. The function which takes C to this element is continuous. This is a special case of the continuity of the functional calculus. Actually, it reduces to the continuity of the square root. This function is continuous, and since the modulus of U is 1, it follows that we can always find such a delta. Okay, so this was a preliminary step. Now let's try to approximate U. First of all, we approximate U by some element. So we want to approximate it by a unitary element. First of all, we approximate it by an element which comes from AI for a suitable I. So there is an element I in I, such that, and let's denote it by B in I, such that u minus phi I of B is less than delta. For the simple reason that the union of the images of phi I, of the elements phi I, is dense in A, just by the construction of the inductive limit. So this element is invertible because of this. This element is invertible. In general, the element B itself is not invertible, is not necessarily invertible. But we can make it invertible by using lemma 4. So applying lemma 4 to the element phi I of B, we find an index J, which is greater than or equal to I. The element, let's denote it by C. Oh no, C is here. Okay, let it be D. Phi I J of B is invertible in AJ. Also, by the commutativity of the respective diagram, we see that phi J of D equals phi I of B. Okay, so now the advantage of this element G is that it is invertible. And now let's make it unitary. Let V denote the unitary element in AJ, which appears in the polar decomposition of D. That is, this is D times the absolute value of D inverse. So this is a unitary element in AJ. And if we apply phi I to V, so let's denote this element by C for convenience. This is the image of D. So this is C times the absolute value of C inverse. Actually, there is a little exercise here to prove this equality. Basically, it states that phi I commutes with the modules, with the absolute value. And this reduces to the fact that unit of star homomorphisms between C-star algebras commute with square roots. But this is a simple exercise. Actually, unit of star homomorphisms commute with the functional calculus. So in particular, they commute with square roots. Okay, so now let's see that this element phi j of V is close to U. So U minus phi j of V. Let's estimate this as follows. This is U minus C plus C minus this element, phi j of V. So U minus C is here. So this is C. U minus C is less than delta. And this can be estimated as the norm of C times the norm of 1 minus this element. This is less than epsilon because of this. So the whole sum is less than delta plus the norm of C times epsilon. And finally, the norm of C. The norm of C by the triangle inequality is less than 1 plus delta. The norm of U is 1. So this is less than delta plus 1 plus delta epsilon. Well, finally delta is less than epsilon, so the whole expression is less than 3 epsilon. Okay, so this shows that we have approximated U by the image of a unitary element in AJ, and this completes the proof. Now, we want to do the same thing for projections. Lemma 6. The set of projections in A is equal to the closure of the images of the sets of projections in AI. Again, it's clear that the right-hand side is contained in the left-hand side for the same reason. So unital star homomorphisms take projections to projections, and the set of projections in A is obviously closed, so we have this inclusion. So we want to prove the opposite inclusion. So we start with a projection P in A, and a positive epsilon. And we find a positive delta. Again, it's useful to assume that delta is less than epsilon, such that if C is close to P, then C squared is also close to P. Да, конечно. Вот C. Вот оно. Просто вот это вот здесь написано. Это просто обозначено. This is our notation. Okay, so we find delta in such a way that if C is close to P, then C squared is close to P squared. That is, C squared is also close to P, because P squared equals P. This is simply the continuity of the function which takes C to C squared. The same trick as here. So here we consider this function. Here it is convenient to consider the function which takes C to C squared. So, and again, the first step is to approximate P by the image of some element, not necessarily a projection, and then to modify this element to make it into projection. So first we approximate P somehow. So we find an index C, an index I, sorry, such that, and an element A in AI, such that P minus phi I of A is less than delta. First of all, let's observe. We assume that A is self-adjoint. Because if it is not, then we simply otherwise we consider the element A plus A star. So it is self-adjoint and satisfies the same estimate because P is self-adjoint. So we assume from the very beginning that A is self-adjoint. So we apply this this estimate to phi I of A. So this property holds if C equals phi I of A, and combining these two inequalities. So let's denote this line by star. So by star, we see that phi I of A minus phi I of A squared is less than 2 epsilon. This is less than delta, and so it is less than epsilon. This is also less than epsilon, so this is less than 2 epsilon. So phi I of A is not a projection, but it is almost a projection. This is true for A itself, but we can now I call minus phi of j j, and we have this inequality, the same inequality in AJ. Why is it so? This is true because let's recall that this norm is actually the infimum of these norms, just by the construction of the norm on the inductive limit. So since the infimum is less than 2 epsilon, we can always find an element in here which is also less than 2 epsilon. Okay, so let's denote this element by B. B is phi I. So we know that B is almost a projection in the sense that we have this inequality. And the image of B in here is equal to phi I of A just by the commutativity of the diagram. So we may replace here phi I of A by phi j of B. And we see that P minus phi j of B is less than delta. Is it delta? Yeah, this is delta. Is less than delta. Simply because phi j of B equals phi I of A. Okay, so B is not a projection, but it is almost a projection. So the next step is to make it into a projection by using the functional calculus. So that by one of the fundamental properties of the functional calculus, this norm is equal to the supremum of T minus T squared, where T runs over the spectrum of B. This is because the functional calculus is an isometric map from the algebra of continuous functions on the spectrum of B to our algebra. So this supremum is not epsilon. Sorry, this was it 2 epsilon? Yes, 2 epsilon. Sorry, this is not essential, but nevertheless 2 epsilon. Okay, so this is less than 2 epsilon. Let's draw a picture. So this is the graph of the function t minus t squared. This is 2 epsilon, this is minus 2 epsilon. So this is less than 2 epsilon whenever t is in the spectrum of B. And so this implies that the spectrum of B is concentrated in the union of two intervals here and here. So let's write this down explicitly. So this follows that if epsilon is small enough, then, well, actually it has to be smaller than the maximum of this function, which is 1 over 4, but this is not essential. If epsilon is small enough, then the spectrum of B is contained in the disjoint union of two closed intervals, K1 and K2. So K1 is interval of the form from minus beta to beta, and K2 is the interval from 1 minus beta to 1 plus beta, and they are disjoint, so beta is small. And beta, of course, it depends on epsilon. it goes to 0 as epsilon goes to 0. So this is beta. And this is minus beta. Actually, we could easily calculate beta explicitly, but this is not essential. The explicit formula for beta is not essential. What is essential is that beta is small whenever epsilon is small. This is K1, and this is K2. So how we can now make B into a projection? Well, this is very easy. We simply apply the characteristic function, the indicator of the second interval. Let Q be the following element of our algebra J. Well, this function is continuous on the spectrum because the spectrum is the disjoint union of such intervals. And it is a projection in the algebra of continuous functions on the spectrum. It implies that Q is so Q is a projection, and it's close to B. Q minus B. So again, by the fact that the functional calculus is isometric, it follows that this is equal to the following supremum, where T runs over the spectrum of B. And this is also small. Let's draw the picture again. So this is K1 and this is K2. This is T, and this is the characteristic function. So clearly the supremum is at most delta, at most beta, at most beta. So the final step is to observe that the image of Q is close to P. So P is our initial projection, and this distance can be evaluated as follows. This is P minus phi j of B plus phi j of B minus Q. P minus phi j of B is less than delta. So in particular, this is less than epsilon, because delta is less than epsilon. Phi j is of course contractive because it is a star homomorphism between C-star algebras, and B minus Q is less than beta. But beta is small whenever epsilon is small, so this goes to 0 as epsilon goes to 0. So in summary, we see that this is as small as we want. And this completes the proof of lemma 6. Combining these two lemmas, we can now approximate, which is essential for K-theory, we can approximate pairs of unitarily equivalent projections. So let's introduce some notation. Let U, P, R of A denote the set of all pairs of unitarily equivalent projections in A. So it's obvious that if we have a unital star homomorphism, phi from A to B is a unital star homomorphism, then phi cross phi takes UPR of A to UPR of B, because unitary elements go to unitaries and projections go to projections. Lemma 7 is actually a combination of lemmas 5 and 6. And it says that the set UPR of A is contained in the closure of the images of sets UPR of AI. That is, every pair of unitary equivalent projections in A can be approximated by the image of a pair of unitarily equivalent projections in a suitable algebra AI. It would be nice to have an exact equality here, similarly to lemma 6 and 5, but actually I don't know whether or not this set is closed. Maybe it is. What we need is the inclusion, but probably, it is possible that actually these two sets are the same. The proof is just a combination of lemmas 5 and 6. So we start with a pair of unitarily equivalent projections, P and Q, UPR of A. So they are unitarily equivalent, so Q equals U inverse, where U is a unitary element in A. So again, we see that for every positive epsilon, we can find a positive delta, such that if P prime is another projection in A, and U prime is another unitary in A, and P prime is close to P, and U prime is close to U, then U prime, P prime, U prime inverse is close to Q. Simply because Q equals this element, and the respective all algebraic operations in our algebra, including the operation of taking the inverse, is all these operations are continuous. Okay. So now we apply lemmas 5 and 6 and approximate P and U. By using lemmas 5 and 6, we find an index I, a projection pi I in AI, and a unitary element UI in AI, such that phi I of the image of Pi is close to P, and the image of Qi is close to the image of Ui is close to U. Formally, we have two indices, I and J. Here we have I and here we have J, but since our pose set I is directed, we can find an index which is bigger than I and J and replace these two indices I and J by any index which is bigger. So we can assume that this index is equal to this index. So they are in the same algebra, AI. Oh, by the way, delta, for technical reasons, is, as before, we assume that delta is less than epsilon. Okay, so now, if we substitute here phi I of U and phi I of P, respectively, we see that well, first of all, phi I of Ui, phi I of Pi, and Ui inverse is close to Q. less than epsilon. So if we now denote this element by qi, so we see that pi and qi are unitarily equivalent. The image of pi is close to p, and the image of phi I is close to q. And that's it. So this completes the proof of lambda 7. Okay. To apply our results to K-theory, we need to make one more step. We need to extend these results to matrix algebras over A, because K-theory is defined in terms of projections and unitaries in matrix algebras. And towards this goal, we will show that the operation of taking the matrix algebra commutes with inductive limits. Actually, we will prove a slightly more general statement, which states that the maximal tensor product of C-star algebras commutes with inductive limits. We start with the following simple observation, lemma 8. If we have three C-star algebras, A, B, and C, and we assume that A and B are unital, then there is a natural bijection between the set of all unital star homomorphisms from the maximal tensor product of A and B to C. So here UC star is the category of unital C star algebras. Well, C is not necessarily unital, so we just consider all star homomorphisms, not necessarily unital. And the set of all pairs, phi psi, where phi is a star homomorphism from A to C, and psi is a star homomorphism from B to C, such that their ranges commute. By the way, commutes with psi of B for all A and B. And explicitly this bijection takes every star homomorphism F from the tensor product to C to the pair phi psi, where phi is given by the following formula. This is F of A tensor 1, and psi, similarly, psi of B is F applied to 1 tensor B. Here it is essential, of course, that A and B are unital. Well, the proof is very easy, because it's clear that if F is a star homomorphism from here to here, then clearly we can construct phi and psi in this way, and indeed their images commute, for the simple reason that these two elements, A tensor 1 and 1 tensor B, commute in the tensor product. So clearly we have the map from here to here. And conversely, if we have such a pair, given such a pair, phi and psi, we define a map F to C by the following formula. It takes every elementary tensor to the product phi of A, psi of B. So by the universal property of the algebraic tensor product, it uniquely extends to a linear map from here to here. And since the images of phi and psi commute, it follows that F is a star homomorphism. Since phi of A commutes with psi of B, it follows that F is a star homomorphism from the algebraic tensor product of A and B to C. And now by the universal property of the maximal tensor product, it follows that F uniquely extends to a star homomorphism from the maximal C star tensor product. It uniquely extends to the maximal tensor product. And that's it. So now we show that the maximal tensor product commutes with inductive limits, at least in the unital case. This is lemma 9. For every unital C star algebra B, there is a natural isomorphism between the inductive limit between A tensor B, between the maximal tensor product of A and B, and the inductive limit of AI tensor B. To prove this result, let's first of all observe that this tensor product, well, first of all, we observe that AI tensor B, these algebras form an inductive system with the following connecting maps. We simply tensor phi ij by the identity map of B. So this is an inductive system. And A tensor B, together with the maps phi I tensor 1, this is an inductive cone. Inductive cone over the system. So we simply check the universal property. So we will want to show that this inductive cone is the initial object in the category of all inductive cones. So we take another inductive cone, let's denote it by C, with the structure map psi I. Be another inductive cone over the same system. So we draw the respective picture. This is C. This is here we have AI tensor B, maximal tensor product of AI and B, AJ and B. This is the structure map phi ij tensor the identity map of B. And here we have psi I and psi j. So this diagram commutes whenever I is less than or equal to j. So C is an inductive cone. Well, since our algebras are unital, we may embed AI into the tensor product of AI and B by the following simple formula. And similarly, we embed B into the same tensor product. So for convenience, we identify AI and B with the respective subalgebras of the tensor product. So the first observation is that if we restrict everything to AI and J respectively, then the initial inductive system AI. So C together with psi I restricted to AI is an inductive cone over the inductive family AI phi ij. Just by the commutativity of this diagram. And by the universal property of the inductive limit, we deduce that there is a unique map from A to C. There is a unique star homomorphism phi from A to C, such that phi composed with phi I is psi I restricted to AI for every I. Similarly, let's now restrict everything to B. And if we restrict everything to B, we deduce that phi I restricted to B equals phi j restricted to B, just by the commutativity of the diagram. Well, this is true whenever I is less than or equal to j, but since our post set I is directed, we have the same equality for all pairs I and j. Just choose k which is bigger than I and j. And so we can define a homomorphism psi from B to C by the following simple formula. We simply restrict psi I to B, and this doesn't depend on the choice of I. So we have a pair of homomorphisms from A to C and from B to C. We want to show that their images commute. But first of all, let's observe that phi of A commutes with psi of B if A comes from AI and B belongs to B. So this follows from this equality. Well, indeed, from AI, the fact that these two elements commute follows from the fact that so the images of AI and B in the tensor product commute. So psi I takes them to the elements which commute in C. So these elements commute, but since the union of these images is dense in A, we deduce that the same is true. The same is true for all elements A and A. So we can apply lemma 8 and find a unique star homomorphism F from the maximal tensor product of A and B, which satisfies the following equation. This is psi I. This is phi I tensor the identity map, and this is F. So why does it commute? Observe that this diagram commutes if and only if we have this relation. That's denoted. So this is equivalent to this relation. Well, indeed, this property holds if and only if it holds if we substitute for A an arbitrary element which comes from AI. In this case, this equality just reduces to the commutativity of this diagram and the other way around. So these two properties are equivalent. So in summary, we see that F is a morphism of inductive cones, and it is unique. It is unique because of the uniqueness here. So it is a unique morphism of inductive cones from A tensor B to C. And so A tensor B is just the inductive limit of the respective sequence, of the respective inductive system. By the way, it's rather easy to extend this result to the non-unital case. This is a simple exercise for you. By using unitizations, extend this result, extend lemma 9 to the non-unital case. So now, as a corollary of lemma 9, we see that the matrix algebra Mn of A is isomorphic to the inductive limit, of course, this is star inductive limit, of the matrix algebras over AI. Simply use lemma 9 in the case where B is just the matrix algebra over the complex numbers. And of course, let's recall that there is a unique C-star norm here on this algebra. So it is equal to the maximal C-star norm on the tensor product of A and Mn. Okay, so now we are ready to prove our theorem about the continuity of K0. Oh, sorry, one more little remark, lemma 10, which is very easy. Lemma exercise 10. If A is a C-star algebra, if A is a C-star let's assume it is unital, A is a unital C-star algebra, then for every projection P in R, in A, the norm of the element 2P minus 1 is equal to 1. This is a simple calculation which involves the C-star axiom. And second, if you have two projections P and Q, and the distance between them is strictly less than 1, then they are unitarily equivalent. Well, actually, one, as I have already said, that one is a simple application of the C-star axiom, and the two follows from our earlier results about idempotence. So some time ago we proved that if P and Q are idempotents, and this number is less than 1 over this norm, then P and Q are similar. But this norm is equal to 1, and we already know that two projections are similar. Actually, two self-adjoint elements are similar if and only if they are unitarily equivalent. So this is just a combination of what we already know. Okay, we can now prove our theorem about the continuity of K0. Proof of theorem. So we want to show that alpha is an isomorphism. First of all, we prove the injectivity. The injectivity of alpha. Oh, no, sorry. Let's start with the surjectivity. It is a bit easier to prove the surjectivity. Surjectivity of alpha. Well, A is unital, and K0A is generated by classes of projections. This is true for any unital C-star algebra. It suffices to show that for every projection P in A, the class of P in K-theory belongs to the image of alpha. Because every element in here is a difference of the classes of two projections. Well, okay, so we apply our lemma 6 was it lemma? Yeah, this was lemma 6 about approximation of projections, and find an element I in our post set I and a projection Q in the algebra AI such that phi I of Q is close to P. In fact, it suffices to find Q in such a way that this is less than 1. And we now apply lemma 10. So these are two projections. The distance between them is less than 1. Lemma 10 implies that they are unitarily equivalent. Phi I of Q is unitarily equivalent to P. And so they have the same class in the K-theory. So this follows that P, the class of P, is equal to the class of phi I of Q. That is to the image of the class of Q under the induced map phi I star. And by the commutativity of the diagram, the image of this arrow is contained in the image of alpha. And so this sits in the image of alpha. And this completes the proof of the surjectivity. Oh, sorry, of course, note of A. Of course, here we have to work in with the matrix algebra. Sorry, let me correct this. So P is in the matrix algebra, and Q is also in the matrix algebra over AI. Mn of AI. Actually, we have used here not only lemma 6, but also a corollary from lemma 8, which states that Mn of A is the direct limit, the inductive limit of the matrix algebras over AI. Corollary together with lemma 6. So I hope now it is correct. Let's now prove that alpha is injective. This is slightly more tricky, but also the injectivity of alpha. So let's take an element in the kernel of alpha, that is denoted by X. So the kernel, so it is a subgroup in the inductive limit of K0 of AI. And since this is the inductive limit in the category of abelian groups, it is equal to the union of the images of the maps alpha I. So every element in the inductive limit comes from a suitable group K0 of AI. So we can write X in the following form. Alpha I applied to a suitable element in K0 of AI. And this element in turn can be written as the difference of two projections, P minus Q. So P and Q are projections in the matrix algebra. Well, we don't know the size, M infinity, over AI. So alpha of X is 0, X is in the kernel. And this means by the commutativity of the diagram that this means that phi I star of P equals phi I star of Q, since the diagram is commutative. Or equivalently, the classes of the projections phi I of P and phi I of Q are the same in K0 of A. Okay, so we can now, without loss of generality, we may assume that these elements are unitarily equivalent. We may assume that phi I of p and phi I of q are unitarily equivalent in the matrix algebra of a suitable size for some m, why is it so? Well, this is a standard trick which we have already used several times. So let me briefly recall how it works. So these two elements are the same in K-theory. This means that they are the respective projections, this one and this one, are stably algebraically equivalent. So first of all, we'll make them not stably but exactly algebraically equivalent by adding the direct sum with a suitable identity matrix of a suitable size. Oh, sorry, not the identity matrix. Yes, the identity matrix of a suitable size. So two elements are stably equivalent if they are equivalent after adding the identity matrix of suitable size. This doesn't change our element x because we add the same matrix here and here. So they cancel. And the next step is to make them not just algebraically equivalent but unitarily equivalent or equivalently similar by enlarging the size of the matrix. So we know that if two elements are algebraically equivalent in m n of a, then they are similar in m to n of a. So again, this doesn't affect the element x because we add the zero matrix here and here. So x will be the same. And so we may assume from the very beginning that these two elements are unitarily equivalent. Of course, and once again, here we use the fact that self-adjoint elements are unitarily equivalent even only if they are similar. Okay, so they are unitarily equivalent. It would be nice to have that p and q are unitarily equivalent. This would complete the proof. In general, this is not the case. So let's introduce some notation. So for every k which is greater than or equal to I, let pk denote the canonical image of p, the image of p in ak. This is phi I k of p. And similarly, qk is phi I k of q. So these are elements in ak. Let's observe that it suffices to show, there is k such that pk and qk are unitarily equivalent. Again, sorry, not in AK, but in the matrix algebra, over AK. So it suffices to show that they are unitarily equivalent if k is big enough. Why is it so? If this is true, if they are unitarily equivalent, then our element x, which is a alpha I applied to p minus q, can be written in the following form. This is alpha k applied to pk minus qk. Because this is an inductive cone over this system. But since pk and qk are unitarily equivalent, so this is 0, and so we see that x is 0. Okay, so we want to show, we want to find such an index k. Let's apply lemma 7. So these two elements, phi I of p and phi I of q, they are unitarily equivalent projections in a man of A. So we can approximate them by the images of unitarily equivalent projections from some algebra AJ. So by lemma 7, there is an index j, and we may assume without loss of generality that j is greater than or equal to I. Again, since our set is directed, we can assume that j is greater than or equal to I. And there are two projections, p prime and q prime in aj, in the matrix algebra over aj, such that they are unitarily equivalent. P prime is unitarily equivalent to q prime, such that phi j of p prime approximates phi I of p, phi I of p. Approximated in this sense, it's enough to achieve that this is strictly less than 1. And similarly, phi j of q prime approximates phi I of p, or phi I of q. Let's now observe that this can be written in the following form. This is phi j applied to p prime minus pj, just by the commutativity of the suitable diagram. So phi I of p is equal to phi j of pj. And for the same reason, this is equal to phi j applied to q prime minus qj. So this is less than 1. And this implies that we can find an index k, which is greater than or equal to j, such that the norm of p prime k minus pk is less than 1. Why is it so? This is true because this norm is equal to the infimum of these norms, gained by the construction of the norm on the inductive limit. This is the infimum of these norms. So since this is less than 1, we can always find a case such that this is also less than 1. And for the same reason, we can achieve that q prime k minus qk is less than 1. And now let's combine our inequalities. And so we apply lemma 10, and we deduce that these two elements are unitarily equivalent. So pk is unitarily equivalent to pk prime. Pk prime is unitarily equivalent to qk prime because they are the images of unitarily equivalent projections. So these two are unitarily equivalent, and so their images in AK are also unitarily equivalent. This is equivalent to qk prime, and because of this inequality and because of lemma 10, these two elements are also unitarily equivalent. QK. And this is the end of the story, because we proved that PK and QK are unitarily equivalent, and we have already observed that this implies the injectivity of alpha. So this is the end of the proof. Well, maybe it's appropriate to draw a picture which represents the proof of the injectivity. So let me try to do it. So we start with a pair of projections P and Q, which sits in AI, and such that their images are unitarily equivalent in A. So we move them to AJ, where J is big enough. This is PJ and QJ, such that, well, these elements, in general, they are not still unitarily equivalent, but we can find another pair of elements P prime and Q prime in the same algebra AJ, so this sits in AJ, such that the image of P prime is close to the image of J prime, and the image of Q prime is close to the image of QJ. So these are these two inequalities. And these two are unitarily equivalent. These two are unitarily equivalent. This doesn't imply that these two are unitarily equivalent. But if we move them forward to AK, we have the following picture. So this is PK and QK. And if K is big enough, then P prime goes to an element which is close to PK. This is PK prime. And Q prime goes to an element which is close to QK. This is QK prime. So they are in the respective unit balls centered and in PK and QK respectively. And so because of this, these two are unitarily equivalent, these two are unitarily equivalent, these two are also unitarily equivalent, and this implies that PK and QK are also unitarily equivalent. So this is a picture which illustrates the proof of the injectivity. Well, in conclusion, let's look at some. Oh, it's time to finish. But if you don't mind, I'll give some just some examples which illustrate, or maybe it's better to postpone it to the next lecture. Huh? Нормально? Okay, so just a few minutes, to give some examples of how the theorem is applied to concrete situations. Actually, let's start with the following simple exercise, exercise, which is quite elementary, but we will use it several times. If we have an inductive sequence, for simplicity, we assume that we're working with inductive sequences. An inductive sequence in an arbitrary category, in the category A. So suppose that A is the inductive limit of this sequence, and phi I are the canonical morphisms from AI to A. So I claim that if phi 1n, which acts from A1 to AN, is an isomorphism for every n, then all structure maps here and all canonical maps phi I, all of them are isomorphisms. All phi ij and all phi I are isomorphisms. Roughly, this means that if we have a sequence of isomorphisms, then the inductive limit is any object in the sequence. And the respective maps are all isomorphisms. This is very elementary, a simple exercise which works in any category. So on our example one is the algebra of compact operators on a separable infinite dimensional Hilbert space. A separable infinite dimensional Hilbert space. So I claim that K0 of the algebra of compact operators is isomorphic to the integers, and moreover, K0 of K is generated by the class of any rank 1 projection P for any rank 1 projection P. Let's recall that we already know that this is true for the matrix algebra of an arbitrary size. We proved this some time ago when we discussed algebraic K0 for arbitrary rings. So we know that this is true This is true for the algebra, for the matrix algebra Mn. Now we also know that K, this was isomorphic to the inductive limit, to the C-star inductive limit of the following chain of algebras, of matrix algebras, where the embeddings are given by the following formula. So now by using the continuity of K0, we deduce that K0 of K is the inductive limit in the category of abelian groups of what? K0 of M1 is the integers, K0 of M2 is the integers, and so on. And what about these maps? Each matrix algebra is generated by a rank 1 projection, but clearly this map, so we see that all these maps are actually identity maps. And by using our simple lemma exercise, we deduce that this is isomorphic to the integers. So this concludes the proof of the first statement, which states that K0 of the algebra of compact operators is isomorphic to the integers. Why is it generated by any rank 1 projection? To answer this question, let's recall that this isomorphism actually is not uniquely determined. That's denoted by star. So let's recall that the isomorphism star comes from an orthonormal basis of our Hilbert space. And the respective maps phi n from Mn, respective map from Mn to K, takes Mn onto the following subalgebra, or the algebra of compact operators, Pn, Kpn, where Pn is the projection onto the linear span of the first n elements of the basis. And in particular, phi 1 from C to K takes the identity of C to P1, to the projection onto the first vector of the basis. And now, of course, we can choose a basis in such a way that P1 equals P. So P is our projection, an arbitrary rank 1 projection, so we find an orthonormal basis in such a way that P1 equals P. So we may assume that P1 equals P. Again, by using our lemma, we deduce that phi 1 star is an isomorphism from K0 of C to K0 of K. This is an isomorphism, and it takes the generator of this group, the identity of the complex numbers, to the class of P because of this. So this class generates this group. And this completes the proof. Ну, K сидит в K с плюсиком. K0. K is not unital, but this is a subgroup in K0 of the unitization of K plus. K plus is unital, and it is generated by projections in matrix algebras over this algebra. And if we have a projection in K, its class
Projection in 1 by 1 matrix?
yeah, K, yes. one by one matrices are of course just the elements of the original algebra. Yeah, I see what the problem is because this class is in here.
The level of modules, can we just say that this is?
It is the one-dimensional. The problem is not in here, but of course at the level of modules this is so rank 1 projection is just the Hilbert space. Sorry, no, it's just the problem is not here. The problem is not is that okay, sorry. Of course, there is no problem here because of course any projection. If you have an arbitrary C-star algebra A, actually any ring A, then if we look at the group which is denoted by K00 in our exercise sheets, this is the abelian group generated by equivalence classes of projections in A. Then we have a natural map from here to K0 of A, which is contained in K0 of A plus. So actually any projection in the matrix algebra over A generates an element in K0 of A. So in general this is not an isomorphism, but we have a map from here to here. And so this projection gives us a well-defined element in here.
So it's one by one matrix?
It's if we want to make it into an infinite matrix, this is the following, something like that.
But not one?
One here, one is here. This is the matrix unit E11, if you like. In M infinity of K.
No.
What's the problem?
Because one is not a projection, one projection. I think we need to replace. It's not an infinite matrix in M infinity. It's one element of infinite matrix.
Well, this is yes, this is not this is in K, and K is contained in M infinity of K. So this is an operator just. This is an operator on our Hilbert space. This is a rank 1 projection.
Yes, okay.
And this is embedded into M infinity of K, if you like. So we can take this matrix and add 0 here, 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 and so on. So this is only the element of K. But any projection in algebra, of course, generates an element of, it generates an element in K0. That's the point. Okay, so now we see that we have calculated K-theory, the K-theory of compact operators, and that's all for today. But you can find more examples in our last exercise sheet. There are many concrete C-star algebras for which we can explicitly calculate the K-theory by using the continuity of K0. In particular, we can easily construct a C-star algebra whose K0 is isomorphic to the group of dyadic rational numbers. This is the so-called canonical anti-commutation relation algebra. We can also easily construct a C-star algebra whose K0 is isomorphic to the rational numbers, again by using inductive limits. And in fact, moreover, by using the inductive limits, we can, for any torsion-free countable abelian group G, if G is countable and torsion-free, we can use inductive limits to construct a C-star algebra A, which is isomorphic to the inductive limit of finite dimensional sister algebras and such that K0A is our group G. So my point is that the continuity of K0 gives us many concrete examples of sister algebras whose K0 is explicitly commutable. Okay, thank you. That's all for today. So at the next lecture, we deduce the stability of K0 from the continuity. So we will show that K0 doesn't change if we multiply our algebra by the algebra of compact operators. And then we began to study the properties of the functor K1.